electrolytic cells. And another blue box, so this actually will be an equation on your test. Now this is the natural log form of the Nernst equation. I love the word Nernst too, Nernst equation. And we're going to look at the log base 10 here in a minute, but this is the natural log form. And what those things mean, the R of course means the ideal gas law constant, and you would use that 8.31 joules per mole Kelvin. T, always temperature is in units of Kelvin. N is the number of moles of electrons transferred during a redox reaction. And then F is that Faraday's constant we ran into before. And of course, Q is that snapshot. Q is your reaction quotient for your equilibrium.
And is that given to us on the table or in the problem?
Q, actually, I'm going to show you where that is. Q is, and you're going to see it here in a minute, like if you have, A plus B, in equilibrium with C and D, we said K is equal to molar concentration of C raised to stoichiometric coefficient times molar concentration of D. Okay, anyway, you get the idea.
Yeah, I'm sorry, I didn't mean to.
That's okay. That. And we said that's at equilibrium, and Q actually, or QC, same thing, is the same thing, but it's not at equilibrium. So actually, we're gonna do 2 problems, and we'll kind of see how Q fits in. The difference between, and I had to go back and forth, the difference between these two is that have taken R value, R has a particular value, F has a particular value, and if we assume it's at 25 degrees Celsius, T is 298. And so if you take those 3 variables and go ahead and divide them out, you get this form of the same relationship. But I mentioned that this is the log form, the natural log form, and what I want to concentrate more on is this form, where the difference here is now it's not the ln of Q, it's the log base 10 of Q. So this value, 0.0592, actually it came from plugging in R, the temperature at 25 degrees Celsius, or 298 K, and and Faraday's constant. So this boiled down to this is what we're going to use for the next couple of problems. So what does it say? It says actually that your cell potential, we talked about E's yesterday, so this would be your E of the cell, is equal to what the E of the cell is under standard conditions, that's what that not means, minus this quantity, 0.0592 divided by the number of electrons that are being exchanged in a redox reaction, times the log of the reaction quotient. Okay. So this is then a way to know what your potential will be, because that's what E's are, what your potential will be under non-standard conditions. Now, standard conditions, we said, had a certain temperature, but we're going 25 degrees Celsius. We're not messing with the temperature. It had a certain pressure. I honestly don't care about the pressure. Do you guys remember we said that standard conditions was 1 molar was your aqueous concentration of aqueous solutions? That's the thing that the Nernst equation fixes. It's not 1 molar. And actually, this Q term over here is going to take that into consideration. And so, if your cell potential, or your overall cell potential, if it's positive, then it will be spontaneous. Your battery will work. If your cell potential is equal to 0, then it's at equilibrium. It means it's going in the forward direction and the reverse direction. And if it's negative, if your cell potential is negative, then your battery is not working. It won't be spontaneous. So let's look at the special situation when it's at equilibrium. So when it's at equilibrium, then like we set up here, then actually your reaction quotient is equal to K, your equilibrium constant. And then that equation that we looked at a minute ago becomes this, where now we can solve for the cell potential under standard conditions. Okay. Oh. All right. So if we take this and rearrange it, we get the log base 10 of the equilibrium constant K is equal to the number of moles transferred, N, times the cell potential under standard conditions, E naught, divided by 0.0592. We're not going to do a problem using that. But this was a figure we looked at the other day. Actually, I think it was maybe just yesterday. We said we can link the equilibrium constant K and Gibbs free energy with this equation. We can link Gibbs free energy and cell potential with this equation. And now we can link the cell potential with the equilibrium constant with this. Which, by the way, this one right here is the same as that last blue one. I'm just plugging in values for T, R, and F. All right. So in all of that mess, what might you run into, or what do I think is important for you to know? Well, let's work a problem. We're going to pick two half reactions. We're going to take silver and copper. Now notice as I have these listed, it looks like they're both being reduced. The +1 to 0, the +2 to 0. And we know with redox reactions, one's going to have to be reduction, one's going to have to be oxidation. I can't remember what. Maybe I don't have that. That's a different type of problem. So in this particular problem, we're going to mess with the molar concentrations. And like I said, I kind of implied or suggested is when you change up your molar concentration from standard conditions, which is 1 mole per liter, to something different than your Q is what's going to bring into effect. So we're going to calculate the cell potentials, E0, at two non-standard conditions. Temperature is fine, but the molar concentration isn't. So we're going to look at these where we have the silver ion at 0.1 and the copper 2.1, and then the silver ion reduced to 0.001 and the copper stays at 0.1. The third thing we're going to do is knock out the value for K. I'll show you what that looks like. So here we go. We actually, back in the previous part, went ahead and made a cell out of copper and silver. And as it turns out, our copper is good at would be the oxidation half cell. The silver would be the reduction half cell. We know that works well because we have a positive cell potential, the most positive we could get with this combination.
So could you check to see if a battery could be formed if like you got a negative potential energy of the cell? Could that tell you that, oh, well, that's not
right?
The other way?
Exactly. Yep. Exactly. If it's negative, then it's not spontaneous.
So you don't even have to do trial and error. You can just look at a list and then pick the ones that work.
Probably. All right. Okay, so in order to, how do I say this? So this up here, what I have on the board here, think of how we would come up with Q. Does this make sense? And I don't think I have this in my notes, but maybe I do. Q, reaction quotient, is equal to the molar concentration of the products raised to the stoichiometric coefficient. So now remember, if it's a solid, it doesn't appear. So we have Q is equal to the molar concentration of Cu2+. Its stoichiometric coefficient is 1 raised to the first power, divided by, divided by the molar concentration of the reactants raised to their stoichiometric coefficient. Now, solids don't appear in your equilibrium constant expression, so it's just simply Ag, and you're in good shape if you forget that squared, because of a lot of us do, but you cannot, because it's the stoichiometric coefficient, and it's the pattern to set up your equilibrium constant expression. So that's the Q in our Nernst equation. So here's our Nernst equation for non-standard conditions. We know the cell potential for standard conditions. That was the number at the bottom right-hand corner of the previous slide. The number of moles of the number of moles of electrons would be 2. Does that seem right? On the previous slide, we saw 2 electrons. 2 electrons, that's N. Okay? And that's E naught. And this Q is going to be this one up here. Okay? That's it. So standard cell potential was at 0.463 volts, we had in the previous slide. 2 moles of electrons are exchanged in this redox reaction. Our Q is, again, it's products over reactants raised to their stoichiometric coefficients. Don't forget this stoichiometric coefficient in front of the silver is 2. Then we're ready to plug and chug. So a value for Q is 0.1 divided by 0.1 raised to the second power, or 10. So then plugging in stuff, it looks like this, where E is equal to that 0.463 minus 0.0592 over 2 times log of 10. Log of 10 is 2. Log of 10, base 10. I should know that. Log of 0 is 1. Log of 1 is... I don't think I brought my calculator. Did you get 1? Log of 10 is 1?
Yeah.
Okay, thank you.
Me, I'm not very good at this stuff. Yeah.
Okay, very good. All right, so here we go. That is equal to 0.433 volts is now the cell potential under these non-standard conditions. And again, non-standard here just means we're messing with the molarity. I'm trying to think, will you always end up with less of a cell potential than standard conditions? And not necessarily. End up with a negative quantity here. I don't know. Which one? Are we ready? Are we ready? So that was the first one. Now, the second one, all we're going to do is going to be very similar pattern, but we're going to change these more. Or was it this one? Let's see, one of them is the same. I think this one's the same, this one changes. So for the second one, yeah, all we're going to do is change the molar concentration of our silver. So again, we're using the Nernst equation, where again, the standard cell potential was 0.463 volts. The number of moles of electrons transferred or given up and released and consumed, 2 moles. But now our Q is 0.10 divided by 0.0010 raised to the second power, which gives you 1.0 times 10 to the minus 5th. So we're going to end up taking the log of that number. So what do you get there?
5.
5, thank you.
I think it's how many zeros there are.
I think it is too.
Like, because 1 is 0, 10 is 1, 100 is 2. So I think it's just like,
Yep,
okay, that makes sense.
I'm liking it. Okay. So here we end up with, and we decided this is 5. Is it? It's positive 5, not negative 5, isn't it? Yep. That's 5. Cool.
I came up with 10,000, so I was like, I don't know what to do that.
So when you put this in your calculator, do your business, you're going to end up with an even lower cell potential of 0.315 volts.
So if you increase the amount, does it increase the potential?
Well, it seems like if we had a ratio, if this was flipped, like if we had 0.0001 here and 0.1 here, If you end up with a negative exponent, then that's going to be a negative number, and then negative times a negative is positive, and then it's going to increase it. Does that make sense? Yeah, so if this ratio is less than 1, which this is much bigger than 1, but if it's less than 1, then actually you're going to increase.
So you have smaller products and more.
Yeah, I think so. Interesting. Okay, so the last question was to knock out the equilibrium constant, K. So yeah, I said we wouldn't be using this, but here we are using this. We are trying to get to K, and remember we said, well, let's plug in first. Let's just plug in your N, which is 2, and your cell potential standard states, which was that 0.463 volts. And if you divide by the 0.0592, you get 15.6. Now we've had to do this before. We're after K, which is the log base 10 of K. Remember, what we got to do is take 10 raised to this power is equal to 10 raised to this power. And then what this becomes is K. Remember that fun little trick? So your K is equal to 10 raised to 15.6. So 10 raised to 15.6 is 4.38 times 10 to the 15. And we talked about large K's, that's pretty large, so it seems like it's pretty product favored. Very good. That's it. Part 6 homework. You're not going to do 7.
Got our last class.
Last class.